Hello friends, so in this lecture we will see the next property of fluid, that is surface tension. So before understanding the concept of surface tension, we will understand some few concepts before the surface tension. So first we have to understand what is cohesion and adhesion. So when we are going to define the cohesion and adhesion, so first we are defining the cohesion. So cohesion is actually the intermolecular attraction force between the two molecules of same substance, or we can say that between like molecules. That if I am saying there is some fluid, so when we are defining cohesive forces, so cohesive forces are the intermolecular attraction force between two molecules of the same substance. That is the cohesive force. Now similarly, if I am defining adhesive forces, what is adhesion is, so adhesive forces are the intermolecular forces between two molecules of different substance. Like here I am defining, if some another type of fluid and there is a molecule here, so this attraction force is the adhesive force. So means, what is the difference between the cohesive force? Cohesive force is the intermolecular force between the like molecules or two molecules of the same substance, and the adhesive force is the intermolecular attraction force between two molecules of different substance. So this force is adhesive force, this force, and this force is cohesive force. Now on the basis of cohesive and adhesive forces, we can define the wetting and non-wetting fluid. That is wetting and non-wetting fluid. Non-wetting fluid. So what are the wetting fluids? So wetting fluids are those which will wet the surface. Wetting fluids are those which will wet the surface, like water. So based on this definition, when I want to define the wetting fluid, so for the wetting fluid that I am considering, there is solid surface here, and over the solid surface there is droplet of some fluid. So now in this case, when this droplet is over the solid surface, so we can consider cohesive forces, that is the intermolecular force between the two molecules of same substance that I am marking here. This is cohesive force. And adhesive force is the intermolecular attraction force between dissimilar molecules between the solid surface and fluid. This is adhesive force. So if the fluid is wetting fluid, in that case adhesive forces will be stronger than the cohesive forces. That is, adhesive forces will be larger or greater than the cohesive forces for wetting fluids. Alright, so in this case adhesive forces are stronger than the cohesive forces. That's why, as this attraction force is larger than this one, this liquid or fluid will try to spread over this solid surface. So means it will take a shape like this one slowly, because the attraction is strong here between these two different molecules, and after some time it will look like this one. So for the wetting fluids, adhesive forces are stronger than the cohesive forces. That's why this fluid will spread over the solid surface, and that is termed as wetness or wetting fluid. There is one more criteria we can provide here, that is, if we see the angle of contact, let if I am making a tangent line to this curvature here, so the angle between this tangent line and the solid surface, that I am saying theta. So for the wetting fluids, this theta will always be less than 90 degree or pi by 2. The angle of contact for the wetting fluid will always be less than 90 degree, and in case of clean glass and pure water, this angle of contact approaches approximately 0. For clean glass and pure water, theta is approximately 0 degree. That's why water is a wetting fluid. Water is a wetting fluid. Alright, now if we are defining non-wetting fluid, so for non-wetting fluid, like mercury, so if there is some solid surface here, and there is some fluid over here, there is some fluid over this solid surface, like this one. If I am saying there is mercury over here, so as this fluid is non-wetting fluid, then this is the cohesive force and this is the adhesive force. So for non-wetting fluids, cohesive forces are stronger than adhesive forces for non-wetting. Right, cohesive forces are stronger than adhesive forces. That's why this fluid will try to contract itself. It will not spread over the solid surface, it will try to contract itself. So means after some time the shape of this fluid will look like this one. It will not wet the surface. It is non-wetting fluid. So in case of non-wetting, cohesive forces are stronger than the adhesive forces. So similarly, if in this case I will try to make a tangent line to this curved surface, it looks like this one. So angle between this line and the solid surface, that is this one, this theta. So theta will always greater than 90 degree but less than 180 degree. Means the range is between pi by 2 and pi. Alright, this is the range here. So means in case of mercury and glass, the angle range is approximately 135 degree to 150 degree. This is the angle range for mercury and the some solid surface. That's why the mercury is the non-wetting fluid. It will never wet the surface, and water is a wetting fluid. It will try to wet the surface. Now we are in position to understand the concept of surface tension. So to define the surface tension, I'm taking this space that I will utilize here. Alright, that is okay. So let I'm considering this is the free surface of fluid. Right, below this one there is fluid here. So this is the free surface of this fluid. Now in this fluid, in the interior of the fluid, let I'm considering a molecule here. This is the element of this fluid. So there is, let I'm saying this is air here, and this fluid is that I'm considering water here. So this is the element of water here. Sorry, that is molecule of the water here. This molecule of water is surrounded by the other molecule of water. So it's obvious when it's surrounded by other molecule of water, then there is a cohesive force in between these molecules. So as this molecule is surrounded by the other molecules, this is in perfect equilibrium. We can draw like that. That if I'm drawing a circle around this one, over this circle periphery there is molecules, and between these molecules there is a attraction force, that is the cohesive force. So this molecule is in perfect balance. This molecule is in perfect balance. Now similarly, any other molecule within the interior of this water has perfect balance or perfect equilibrium. Now let if I am considering a molecule over this surface. So this molecule has other molecules below this one or side by side this one, but there is no molecules above this one. So the cohesive forces that will act on this molecule will look like this one. It's like semicircle, a semisphere if we are seeing the 3D portion. So this is balanced, this side by side. Here is the cohesive force between the molecules. Here is the cohesive force between the molecules. So means this molecule has no other molecule of water above this one. That's why this molecule is not in equilibrium state. The molecules below this one or around here will try to pull this molecule inside the interior of fluid mass. Right. Similarly, any other molecules which are lying on this surface as feeling the same pulling force into the interior of the fluid mass. So due to this case, but we see that this is not happening when there is a free surface of liquid, because if this is happening, then all the molecules on the free surface of fluid will move into the interior of fluid, and you can see the fluid movement here. But in the real life there is no movement of fluid layers or top surface layer into the interior. So why? So if this molecule want to an equilibrium state here, it requires some extra energy here to hold itself here. So this molecule will expend some of quantum energy to balance itself or to maintain an equilibrium state. How? Let's consider like that. Let's consider this is a paper sheet, and you can imagine this is a fluid surface. All the particles are lying on this surface. So let if I am providing a weight here over this surface, there is some weight here, and the weight of this block is acting in downward direction. That's why the shape of the paper will look like this one. I will try to draw this one. due to the weight that is lying here. This will bend due to this weight. If we want there is no bending of this paper, so if you apply a force like that, you can do this experiment simply taking a paper sheet, applying some weight on the paper sheet, and if you stretch the paper in this side, then due to stretching this paper this side or providing tension both sides of the paper, again it will form in this shape, that is straight shape. Now there is a tension force here because you are providing some tension in the paper. Alright, so due to this tension, this paper will not move in the downward direction, it will remain straight. So as this particle has a feeling of downward force, that extra energy expended by this molecule will provide some tension force side by side that will stretch this surface or stretch this water surface, and this stretching is termed as surface intention or simply defined as surface tension, because you are providing surface tension. It is also stretching here, so there is a tension here. So due to this extra energy, a quantum of energy expended by these molecules over the surface will be in tension here. That's the term derived, that is surface tension. So this molecule will be in equilibrium state. So according to our definition, we are saying the molecule of fluid will expend some quantum of energy over the surface. So we can define that is surface tension. Surface tension is energy over the surface area. Right, energy over the surface area. So if I note the energy is joule, area is meter square. So this is the unit of surface tension, joule per meter square, and the notation of surface tension is by sigma. This is joule per meter square, and as we know, joule is Newton meter divided by meter square. So this will out, so we can also define as Newton per meter. So these are two units we can use for the surface tension. One is the joule per meter square or Newton per meter. Right, we can use two units, joule per meter square and Newton per meter. So this is defined as surface tension. So what are the effect of surface tension? So first of all, the surface tension force is very much small compared to the other strong forces like pressure force and gravity force. This force is very much small compared to other forces. Means if let we are saying there is some system, and that system three forces are acting: surface tension force, gravity force and pressure force. So compared to the gravity force and the pressure force, the surface tension force is almost negligible force. Alright, and this force will be this force have significant effect when the boundary dimensions are small. Means when the dimensions will be small, this effect will be significant. As the boundary dimensions are going larger, in that case the gravity force and the pressure force is also going to be larger, because let if we are saying the surface is larger here, alright, let if some container the surface is large, in that case the pressure force will be large, and also if the mass is large, then the gravity force is also large. So if the boundaries are larger, then the pressure and gravity force are larger. In comparison to that forces, pressure and gravity force, the surface tension force is almost negligible. So when the boundary dimensions are small, then this force will be significant force. This force will be significant force. So there are two terms here, that is surface tension force is negligible compared to the pressure force and the gravity force, and this force has significant effect. This force has significant effect when the boundary dimensions are small. Right, so if we want to see the effect of surface tension, we can normally see light objects can easily float over the water, or like insects like mosquitoes can easily stand over the water surface. That is because of the surface tension, because this force is enough to hold the weight of that object or insect. And similarly, antiseptic creams are normally has oily character. This is because if they don't have oily character, the surface tension of the cream will be that much of superior. You required large amount of cream for the small area of wrap. Means if let's say I'm saying you want to spread the cream over this area, so if the surface tension is stronger for the cream, then it will try to contract itself. Let this is the amount of cream, surface tension is superior here, it will try to contract itself because of this force. Because if we are saying that this is spherical, the surface tension is acting over the line like that, so this will try to contract itself, so it required more amount of cream to spread over this large area or this area. So if it has oily character, due to oily character the surface tension is going to decrease. So due to decrement in the surface tension force, the contraction of the cream will be less, and that's why you require less amount of cream to wrap or to spread over this large area. That's why the creams are prepared in the oily or greasy materials. So this is the basically effect of surface tension. Similarly, you can see that is raindrops are generally in spherical shape, that are also due to the surface tension. Why? I said that is surface tension is the energy expended over the area, and nature is the best investor. It will try to invest in such a way that the resistance will be less. Means you can see here, if there is some river that is flowing normally, so river will always find a path in the valleys. You never saw that is river is passing like that over the hills, because in the valleys the resistance is less than compared to over the hills. So nature will always invest in such a way that is the resistance will be less. So as there is a energy investment over the area, so if there is a solo drop of water, so it will take spherical shape, because we know the surface area of sphere is less compared to other shapes. So that's why if the area is less, the energy investment will be less. That's why it will take a spherical shape. Now if we are talking about the raindrop, so let's take an example here. So let I'm considering why this is in equilibrium state. So let I'm considering there is a raindrop or water droplet simply. So under this one there is a water, outside air, and this is the free surface. So surface tension will always occur when there is free surface. This is water here. So the forces which are acting on this droplet is first of all the external pressure force, that is atmospheric pressure force, like that. This is P atmospheric, and this P atmospheric will try to compress this droplet, will try to compress this droplet. Now as there is free surface, so let I'm taking 1/2, or let I'm cutting this droplet here, and I'm drawing here. This is the half of this droplet. So here is atmospheric pressure. This is P atmospheric. And you can see here the surface tension is the line force, that is it is acting over the line, not on the area like other force like pressure force. Pressure force is the area force, surface area force. It will act over the area, that is unit of the pressure is Newton per meter square, but the unit of surface tension is Newton per meter. It is a line force. So as here is the free surface, the surface tension will act like that. This is sigma, surface tension. So you can see here the atmospheric pressure and the surface tension both are trying to compress this droplet. So to maintain in equilibrium state, we require some another force that is against of this force, or that will balance this force. So let there is some inside pressure that is acting over here in this direction against this one. Then this is internal pressure. So this internal pressure is acting over this area on the cut of this droplet. So if we are seeing the equilibrium state, so we can say that this atmospheric pressure is acting over this one. So if you want to calculate the force, we can take the projected area for this semisphere. So the projected area for this semisphere is this one, or if let I'm saying the diameter of this droplet is d, then this pressure force will be equals to, so we can write that is P A, that is atmospheric, P atmospheric pressure into over this projected area, that is a circle. So area of circle is pi by 4 d square. This will try to compress the droplet. Now again the surface tension is also trying to compress the droplet. So this surface tension force is also acting in direction with this one. So we can write that is surface tension, sigma is the surface tension, and it is acting over a line that is the periphery of the circle. So that is pi d, and the resisting force against this force is the internal pressure that is acting over this area. So that is pi into pi by 4 d square. Alright, so by rearranging, let's get me some space here. And some space. All right. So here let rearranging these equations. So we can say PA and PI. So PA minus PI into pi by 4 d square. I'm taking pi this side, plus sigma pi d is equals to 0. Alright, so pi will out, d will out, so we can say that there is PA minus PI d by 4, pi is out, 1 d is out, plus sigma equals to 0. So what will be PI? Pi will be something. This is negative, this is negative, so this is, solving this equation we can say that this is 4 sigma by, this is not Pi actually, this is, sorry, that I'm solving here, that is Pa minus Pi is equals to minus of 4 sigma by d, or we can say that there is Pi minus Pa is equals to 4 sigma by d. So Pi is the internal pressure and Pa is the external pressure, all at atmospheric pressure, that is atmospheric pressure. So sigma, it is a positive quantity, because for the, if we are saying the water droplet, so inside water, outside air, this value is positive, so this is positive, diameter is also positive, so this quantity will always be positive. So as this quantity is positive, we can say this one, that is internal pressure is more than the external pressure, as the difference of Pi minus Pa is positive. The internal pressure is greater than the external pressure or atmospheric pressure. So for a droplet to maintain the equilibrium state, the internal pressure should always be greater than the external pressure or atmospheric pressure, and this is due to this surface tension, because in combination with the atmospheric pressure, the surface tension will also try to compress this droplet. Alright, thank you. In the next lecture we will see the another effect of surface tension, that is capillary effect. Till then, take care of yourself. See you in the next lecture.